Let's look at a three-set Venn diagram question. In the CBSE board exams last year, 53% passed in biology, 61% passed in English, 60% in social studies, 24% passed in bio and English, 35% in English and social studies, 27% in bio and social studies, and 5% in none. Percentage of passes in all the subjects is. We're going to look at two different ways of solving this. First, let's look at how we used to traditionally solve this when we did Venn diagrams in high school. We would draw a three-set Venn diagram for the three subjects. You would also have your universal set. We know that inside the universal is 100. You have your bio, English, and social studies. The sum of all the numbers in the bio segment would be your 53. You wouldn't write it here, you would write it outside. 53. English was 61. Social studies was 60. And then you had all of this additional information. But if you want to fill up a Venn diagram, you always start with the center. And if you don't have the central portion, which is basically the intersection of all three sets, you would just put a variable there and write everything else in terms of that variable. So the number of people who had passed both bio and English was 24. That would be the sum of these two segments being 24, which would mean that the one above would be 24 minus x. 24 minus x. Similarly, 35 passed English and social studies, so that would be a 35 minus x here. And you had 27 passing bio and social, 27 minus x. The sum of these four segments is 53, but the sum of three of those in terms of x would be 51 minus x. So the remainder would be x plus 2. 51 minus x plus 2 would give you 53. Similarly, you have 59 minus x, so x plus 2 will take it to 61. And here you had 62 minus x is the sum of three of the four regions, so the last one had to be x minus 2. And you also have 5% passed in none, so that's outside the union. So basically we have 7 segments whose values are given as expressions of x, and the eighth segment is 5. These 8 add up to 100. So the next thing to do would be to add all 8 including the 5 and equate it to 100. Here we can save a little bit of time by taking, let's say, 61 instead of these 4 segments, right? So you can simply say 61 plus the x plus 2 here plus the 27 minus x plus the x minus 2. This is the union. You know that 5% is outside the union, so the union is 95. And from here you can solve for x to get the answer. Plus 2 and minus 2 will cancel. You basically have 88 plus x minus x will cancel. 88 plus x is 95. X is 7. So 7% passed all three subjects. Now, there is an easier way to solve this question. What if I told you can just, without using diagram at all, just take these numbers and say 53 plus 61 plus 60, these numbers, minus 24 minus 35 minus 27, the next three numbers, plus the unknown intersection is equal to the union 95. You can directly solve this and get x is equal to 7. You don't even need to draw a diagram to get the answer to this. So this, how does this work? This is based on a concept called the principle of inclusion exclusion, and we will discuss that next. Principle of inclusion exclusion, I might refer to it in future as PIE. Let's see how it works. Uh, Before we go into the expression, let's try to understand what is inclusion exclusion, what it does for us. I've drawn here an example of a class of a certain number of students uh, who play football, cricket, and basketball. There are no other games in consideration at this point, and this is the data that we have. As you can see, a total number of people who play football is 8, total number of people who play cricket is 6, and for basketball is 8, right? But if I were to make the claim that there are 22 people who were involved in at least one sport, you would disagree, because these numbers represent the separate strings for each sport. But we know there is an overlap. There are multiple overlaps, right? So this particular person here is being counted as a football player as well as a cricket player. These two people are being counted thrice each, right? When you do this 8 plus 6 plus 8, that does not give you the count of total number of people who are involved in sports, because some people are counted multiple times. Twice as in the case of this person, thrice as in the case of these two people. As a result, this sum of the number of elements of each set will not be an accurate representation of the size of the union. The union will be less than that. So principle of inclusion exclusion is a systematic attempt to remove the double counts and the triple counts. Everything that's counted more than once, can we systematically subtract them back and get an expression for the union? And yes, we can, and that is basically what the inclusion exclusion expression gives us. Let's take another blank Venn diagram and I'll demonstrate what happens. So we have your football, cricket, basketball. I need an expression for F union C union B in terms of the total number of football players, cricket players, basketball players, and whatever intersections that they give us. Let's see what that looks like. If I first add F and C and B, as we have just discussed, this sum is going to be greater than the union because of all the people who are being counted twice and thrice. So what does it look like? If I count all the people in F, if I do F, these regions are counted once, plus C, these regions are counted once, plus B, these regions are counted once. So what you get when you add F plus C plus B is that the people who play two sports, these people are counted twice where they should be counted only once. The people who play three sports, they're counted thrice where they should only be counted once. So what do we do about the extra counts? We subtract F intersection C, which I'm going to write as FC going forward. FC is F intersection C. We subtract FB and we subtract BC. Now FC is these two regions, both will be subtracted. FB is these two regions, subtracted. BC is these two regions, subtracted. So you notice that when you subtract FC and FB and BC, we have taken care of all of the double counts that we had in these regions. That is all fine. The extra, the second count that should have been removed has been removed, but the problem now is in the middle region, there were three, those people are counted thrice, two more times than they should have been, but we subtracted three counts, so we should add it back. And so we have to add back the F intersection C intersection B, and this basically ensures, once you do that, notice that all 7 segments inside the union, I'm not interested in the 8th segment outside the union, the 7 segments inside the union have been counted exactly once by the time we evaluate this expression. And that is all we're trying to do. Except for the part outside the union, the other 7 segments should be counted exactly once. And there are multiple ways of doing this, but this is the standard form. And this is the form that you would find useful in the question that we just discussed, because the data is given in that in the same manner. The question with the past percentages in bio, English and social studies. This was basically what I used to write that single line from which I got x is equal to 7. So that is principle of inclusion exclusion standard form. We'll look at a couple of alternate forms as well. What you just saw was the standard form of inclusion exclusion for 3 sets. That is the example question that we saw, but it's the same principle applies equally well to any number of sets. So A union B would be A plus B, add the singles, subtract the double. There's only one version of a two-set intersection that you have, A plus B minus AB, and you'd be done. And you already know this. The union is equal to A plus B minus A intersection B. We have seen this before. This is PIE for 2 sets. If you wanted PIE for 4 sets, it would be A union, B union, C union, D. Add all the singles, subtract the doubles, AB, AC, AD, subtract BC, BD, CD. Add all the triples, which should be ABC, ABD, ACD, BCD, and subtract the intersection of the 4 regions, which is ABCD, and there's only one of these. So notice that it would work equally well with any number of sets under consideration.